All right, friends. Today we're studying collisions. And we're going to study two things about collisions. One, if momentum is conserved or not. Can you tell me what I have been telling you about momentum and collisions?
No, I don't remember. I'm sorry.
Okay.
Momentum and collisions. Inelastic or elastic collisions. Inelastic is when there is not a bounce, so there is not momentum.
Your first statement was right. Inelastic is when they don't bounce. So here I have highlighted I can see you. I have highlighted the equation. What do we call this equation that I have here? What is this equation called?
Force equate both.
Newton's third law.
So close.
Second. You were real close, man.
She bracketed it perfectly. First, third. It's the second. If you take the average, bueno. Newton's second law. The lower one, the one that's highlighted in yellow, is simply multiplying both sides by delta t. So we have the change in momentum is the net force multiplied by the change in time. Because this has come up multiple times, let's review. What does the arrow mean on top? Vector, that it has direction. So your momentum vector is P. What does the triangle here mean?
Delta.
Okay, so delta is change in, which always means final minus initial. So this is saying the change in momentum is the net force multiplied by the change in time. So momentum would be conserved. Conserved means it doesn't change, or delta P is 0, if either the net force is 0 or if the time is 0. And so our collisions occur in a very short time frame. And so we approximate that delta T is approximately equal to 0. So delta P is approximately equal to 0 during the collision. Not before the collision, not after the collision. So in our lab today, we're going to be very careful to only look at the momentum just before they collide and just after they collide. But that's talking about momentum. We also have energy. And we talked about two types of energy in class yesterday. Kinetic energy, energy because something is moving. And so I wrote the equation for kinetic energy here because we didn't have that equation. We didn't get that far in class yesterday. Kinetic energy is 1/2 mass times speed squared. Or you could take that, and since momentum is mass times speed, well, mass times velocity, it turns out, you can also write kinetic energy as momentum squared divided by 2m. That's another valid equation for momentum, kinetic energy. The energy something has because it's moving. That's one type of energy. The other type of energy is potential energy. Potential energy for gravitational potential energy caused by gravity, it's mass times g, the acceleration of gravity, times elevation. So if I take our phone, compared to the tabletop, right now it has 0 potential energy. Right? Because it's not going to move because of gravity. But if I take it up here, it now has potential energy to grab back to the ground.
I trust you.
Unwise. It now has gravitational potential energy. If I were to let it go, it would fall. It would do something because of gravity. So that's the potential energy. So if I take this, if I hold it up here right now, what kind of energy does it have?
None.
Gravitational
potential.
Potential, not full.
If I let it drop, what kind of energy will it have?
It is kinetic?
Kinetic, yes. Okay. So it'll convert that gravitational potential energy into kinetic. Then when it hits the ground, it'll bounce back up, right? Yeah. One of our fundamental rules in physics is energy cannot be created or destroyed. It can be moved from one type to another. So for instance, right now I'm speaking. The sound waves are a form of energy. The light coming from these lights is a form of energy. The heat that travels to us is a form of energy. So we can change the type of energy, but we can't create or destroy it. So if I drop this, it's going to convert which type of energy does it have now?
Kinetic.
Right now.
Gravitational
Potential. But it'll convert it into kinetic. And then when it hits the ground, if it bounces up, if it doesn't change energy, when it gets back up to stopped, it'll have no kinetic. What should its gravitational potential energy be compared to when it started?
Lower?
In reality, it's going to be lower because we're going to lose some energy to things like sound and it, heating up. But in a perfect world, they come back to the same height. But this would never bounce to a higher elevation, right? You're never going to take a Super Ball, drop it, and bounces up higher than you let it go.
So it'll always be equal to or lower than.
Right. So that brings me to this. Now notice this is not a single ball. I'm going to drop it, and I want you to observe.
Yes. Okay.
Did that do what we expected?
No.
Okay, Vanessa says no. What did it do that was different than you expected, Vanessa?
It went higher.
This went higher. What about that? It didn't.
This was a lower question.
So it was, yes. So based on what you saw, what do you think happened?
The energy. Yeah.
Energy was transferred from these balls to this ball. So this ball, it didn't have more energy than the whole thing did. But it had more energy than it had initially, so it went flying up. Now this is another fun example. This is just a half of a ball. If I push on it, I can put a force and it'll move parallel to my force. What do we call it when I put a force and it moves parallel to that force?
Can you give us the first letter?
W.
W?
Yep.
Wait. No.
Wait. Force times the distance parallel to that force.
How would it know?
You should. It's work. Work is a force times distance parallel to that force. And when you do work, you're transferring energy. So when I do this, I'm transferring energy from my body into this plastic. And now I set it on the tabletop, and what's going to happen? What's going to happen when I put it on the tabletop? If I do it right, it'll stay like that for a little bit, and then it shoots up. Okay, it's the first time you do it, which I did before you guys got here, it takes forever, and then it goes quicker and quicker. Why did it bounce up?
Parallel. Energy.
It had energy, potential energy, stored as a spring. It was stretchy. And it was storing it that way. And then when it released it, all that energy went into what type of energy? Kinetic. And so it went flying up with kinetic energy, but then as it's flying up, what happened to that kinetic energy? It went down. It went into gravitational potential energy. Okay, enough playing. We are also going to be looking at energy in collisions. So if I have a cart going down the track, it has which type of energy? Kinetic, because it's moving, right? So it has kinetic energy. When we talk about collisions, the difference between elastic and inelastic is about conservation of kinetic energy. Total energy is always conserved. But we're going to look at kinetic energy. So if kinetic energy is conserved, we call it elastic. If the kinetic energy drops, then it's inelastic. And we're going to examine what types of collisions have conserved kinetic energy and what types have conserved momentum. So here's what we're going to do. First, you need your track set up. Now, Nathan and I set these up, but one thing we didn't do is pay attention to which sensor was which. So look at your system, and motion sensor 2, the motion sensor 2 that is on the left end of your track. So as you're looking at the track,
Your left or our left?
your left. So if you look to the left, that should be plugged into number 1. Is it? Is yours?
Yes.
That one?
The one on your left, that's your right.
So
Is
that one?
that plugged into number 1?
Yeah.
No. That one's plugged into number 2.
Okay, so you need to switch them.
Are you trying to trick us?
No, I'm trying to make sure you're not
Are you trying to
confused.
trick us?
I have a 50-50 chance of getting it right, and I know. So that's all it is.
So they should be in 1 and 2. Okay? Now, we need to level the track first. So how do we level the track?
Ball.
Yeah, the ball and the little feet, adjusting the feet. So I'm going to do mine because I'm going to take 1/3 of all of the data done in lab today. Each one of you will do 1 set, and I will do 2 sets. Actually, is that 1/3? 1, 2, 3, 4.
I
Yeah.
have a question.
Yes.
Is this the longer lab?
This is not a long lab.
I just-
Okay, so I put this on here, and it's rolling a little bit that way, so I'm just going to raise this just a little bit.
I built the shelf once, but it came out like this.
A shelf?
Yeah.
Which lab is the one that we're here for years?
I wasn't paying attention.
I don't know.
My dad got the dog. Great, cool. Good dad.
Okay.
No.
So that's pretty close to level now. So that's the first thing you need to do is make sure that you do level your track. Then our instructions say with just 1 card in the track. So I just have 1 card here. Start the experiment and push the cart at a reasonable speed so it goes from one end of the track to the other. Observe the graphs produced. You should have 2 lines exactly on top of each other for each graph with a third at twice the height. If they're not that way, you have a problem. Now, I'm not going to do it exactly as instructed because I want you guys to go through and answer the questions without me having answered them already. So what I'm going to do is figure out, this is it. Well, I already did this. I just started with it here and I moved it manually up and down the track. And I made sure that my 2 lines were indeed on top of each other with the third one equal to double.
So we do 1 card first, and then we go do the other card?
No, you're just doing it with 1 card, not doing it twice. The reason for this is primarily to make sure that your sensors see the parts all the way down the track. If they don't, adjust the angles of the cards and try it again. But then you do have a question to answer on that. So your question to answer is, look at the lines for cart 1. Was momentum conserved? How would you determine if momentum was conserved?
We have to do it first. We haven't done it.
Oh, okay. I was like,
Girl, if it hits something.
Not if it hits something. What does it mean to be conserved? No,
Yeah, breathe in.
Nathan didn't connect it apparently. What does it mean for quantity to be conserved?
Means it's gonna be a smaller line? I don't know, I'm guessing here.
Conserved means it didn't change. So you're going to check and see if the momentum that you started with was the same as the momentum you ended with. If it starts and ends at the same level, then it was conserved. If it's higher on one side and lower on the other, then it wasn't conserved.
Okay, that makes sense.
Then it asks you the same thing, was kinetic energy conserved? So if we look at what you have on Capstone, the upper graph is showing momentum. Come on. I'm just trying to move this. The upper graph is showing momentum. The bottom one's kinetic energy. So you're answering for momentum, saying, was the line the same level on the start and end sides? For momentum, the second one was the kinetic energy line, the same level on both sides. So you answer those 2 questions, but then there's a third question to make sure you didn't guess. Explain how you got your answers from the graphs. That is what you observed on the graph that told you if momentum was conserved or not, if kinetic energy was conserved or not. And then, well, actually, the first one is theory.
ours isn't working.
What's not working?
We can't click play. I mean, record.
Turn it on.
We don't.
No, not done. All right. So after you've done that, then we're going to be ready to start the experiment. The real experiment. So the first thing you have to do with the real experiment is have your two carts and have their real masses. Now, this is where I need you to make some choices. Each individual needs to choose 1 through 6. So I'm just going to poll you and write your name with the one you choose. So Josie, which one do you want to do?
Number 1.
Okay. Annabelle, which one do you want to do?
4. 4, 2. I don't know.
Nathan, yeah, we'll help us back here, so won't worry.
And Vanessa?
3. I don't understand.
Not yet, Nate. They should be paying attention right now. Okay, so you guys are going to do numbers 1 through 4. That means I'm going to do numbers 5 and 6 here as I'm going through showing you how we're doing this.
All right.
Ready?
So, you guys ready for me to do numbers 5 and 6? Apparently not.
Right now?
I guess I should have pressed.
Yes, right now.
Okay.
Okay, so you're with me, Annabelle?
I don't think my graphs are.
Okay, so I'm doing first number 5. Number 5 is unequal mass, carts approaching at similar speeds. So the first thing I need to do is to set my masses. So here we have how we set the masses. Now I'm unequal masses, so I'm going to put this bar in the cart that is on your left. The cart that's on your left, because that's the one going into passport 1, that's cart 1. So I'm going to put that in here. So my cart 1 has a mass of 1 kilogram. Because remember, the cart is a half kilogram, the bar is a half kilogram.
So when we do our first run, we're just making sure that our graph is working correctly.
The one that I've already talked my way through, yes.
Right. Okay.
Yeah, that's just making sure that everything's graphing right and then answering a question about what's happening. Wait till we're... You first of all need to do the entire track, not just half the track. Okay, but let me do this so we can get started with the experiment. So I need to now tell the computer what my masses are. So tell the computer what the masses are. See where it says calculator, the blue button over here on the side? I clicked that and it opened up the calculator. Right now it has both mass 1 and mass 2 set at 1 kilogram. What is my mass 1?
500.
500.
Mass 1,
10,000.
for the case
1,000.
I'm doing, it said unequal masses. And so I put a bar in here, so cart 1 is 1 kilogram. Cart 2, how did I know which one was 1 and which one was 2?
Because 1 goes into the number 1, it's the left. It's the one that's always.
It's the one that's on the left. The one on the left is cart 1. That is the only rule for deciding which one's cart 1 and 2. So cart 2 is only 500 grams or half a kilogram. So I'm going to click here on cart 2, click a second time, and I'm going to change that from 1 to 0.5. Hit return, and now you can see my graph instantly changed because it now changed the calculation. You can see here the calculations from the one it's on down. It's calculating momentum and kinetic energy. So now I can close this. Now I'm going to simulate my experiment. Now to simulate my experiment, I need my partner. So Nathan, I need you. So Nathan and I are going to, after I start it, go to that one. He's going to push that one, and I'm going to push this one. We're going to, don't try not to crash. Yeah.
Sorry. I thought I hit it really soft.
We're going to push these at the same time and try to get them about the same speed. So, we'll see. We'll probably do a really bad job the first time because we have, that's not what's supposed to happen. Because we have no coordination. So you ready, Nate? Mm-hmm. Okay. Go. Okay. First thing we had a problem was we were going too fast total. They bounced off each other and didn't stick. We had the Velcro set, so they should have stuck. Second problem is I didn't pay attention to which type it was supposed to be. Is it supposed to be sticking or not sticking? Well, we have, oh, yeah.
Are we drawing our lines on our momentum and stuff?
This was supposed to be inelastic. Good. Yes, I forgot that. I should read through these. So these were supposed to be inelastic. They're supposed to stick together, but Nathan and I pushed them too hard. So if they bounce like that, failure, do it again. Yes.
Do we have two of these charts when we're doing ours and our partners, or we're doing yours?
You have two, one for inelastic and one for elastic, but you're only doing yours. So you'll have one graph, your partner will have a different one.
Okay, because like I'm doing number 1, so my graph is going to be number 1.
Yeah.
Your Annabelle's graph is going to be number 4.
That's exactly right. That's exactly right. So let me read through this so I don't. Before doing an experiment, right, you asked me and I forgot to check this. Before doing an experiment, select one of the 6. We've done that. And explain what you think you'll observe.
Can you tell me what page you're on?
This is page 2 right here. Bottom of page 2.
Correct. So I'm just double checking. All of this one is going to be mine, and all of this one is going to be Annabelle's. We each have a paper.
Incorrect. Everything in your lab report is yours.
Okay.
Everything in Annabelle's is hers. So they're going to be different.
They're just going to be different graphs.
They're going to be different graphs, right?
So this whole stack is yours for your number 4.
Okay, so I am supposed to predict what I think they're going to look like. So we have here on the graph supplied, sketch what you think the 3 lines will look like for both of them, and then I explain. So I, being a teacher, I should know what they're going to do. But you know what? You're predicting. So let's go through this predictive process. We have cart 1 is going to the right, cart 2 is going to the left. So one's going to have a positive momentum, the other one a negative momentum. And if we push them about the same speed, because my cart 1 has twice the mass, its momentum should be about twice as high. So I expect cart 1 to be like this and cart 2 to be like that, about half as much, one positive, one negative. Then when they collide, they're supposed to stick together because that's what the inelastic case is. So they're going to end up at the same speed. If I have one heavier one and one lighter one, and they stick together, what do I expect them to do? Do I expect them to move the direction of the heavier one or the lighter one? I expect the heavier one because it had twice as much momentum. So I expect when they hit,
What you said makes sense. You just want worded the same way.
I expect when they hit that it's, I should have used a different color here. Change color.
Okay. You said it makes sense. You just didn't word it correctly. Oh, okay.
So I expect when they hit, it's going to look something like this.
Oh, see.
So that's what I expect to happen for the momenta. Now I go to kinetic energy. Now remember, kinetic energy is 1/2 mv squared. But they both are starting with the same speed again. So I expect, now kinetic energy, 1/2 mv squared, it's a scalar. There's no such thing as a negative kinetic energy. They're both going to have positive kinetic energy, but the one with twice the mass will have twice as much. The one with less mass will have half as much. When they collide, what's going to happen?
They're going to collide slowly.
Well, they're going to stick together, and so the red one is going to go to a speed that is, according to my picture up here, somewhat less, so it's going to drop a little. And the blue one is going to drop some as well. They won't be the same because the blue one still has twice the mass. And then, of course, there's one more line that I didn't give myself room for because I was thinking this through clearly. The total, what's 1 plus 2? 3. So my graph would be like 3, and then I end with like 0.6 plus 1.2, so 1.8. So I expect it to go something like this.
What's the green line?
The green line is the total. That's adding the two together. So that's what I'm predicting. Here, 1 plus a half is a half, or 1 plus negative half is a half. And so I expect that one to go something like this. So that's my predictions. Go ahead.
Our first drawing is what we're predicting.
It's what you're predicting. And I want you to think it through carefully. As long as your explanation, your graphs show some thought, he's not going to mark you wrong. If they don't show thought, then he'll mark you wrong.
Well, good.
So here I need to specify which trial am I predicting. I'm predicting trial number 5. Trial number 5 is unequal weights or unequal masses
Like I'm doing file number 1.
approaching at equal speeds. So I specified there which one I'm doing, and my prediction is momentum, well, they will come together and travel the direction of of the heavier one.
Are we doing elastic or inelastic?
Both.
Oh. Okay.
So they'll come together and travel the direction of the heavier one. That's my prediction. Will momentum be conserved? I need to determine which one I believe is true. I'm going to circle it. Will kinetic energy be conserved? I circle what I believe they are. My reason? Momentum is always conserved. AL. Always conserved in a collision. And when they stick together, kinetic energy is lost. So I put reasons for my predictions and I circled my predictions. Now we're ready to actually do the experiment. So to do the experiment now, Nathan and I are going to do this a little more carefully. So we need to go slower, go about that speed.
Kinetic energy, you say will or will not?
My predictions are that kinetic energy will not and momentum will. So you got this, you guys suggesting. Okay, so y'all ready for this?
Not really. No.
No? Okay, what do you need me to do for you to be ready?
I'm very confused.
Okay, what are you confused about?
I understand what we're doing, I understand, but so we're having a different prediction for both inelastic and elastic, are the same prediction?
You're going to have different predictions for your elastic versus inelastic. The inelastic is first, and then you have, if you look at your pages, you essentially have what looks like the same pages that's changed from inelastic to elastic.
And inelastic is?
Inelastic is they stick together. Elastic is they don't stick together. Okay, so here we go. So I'm going to start it here. There's no rush. Ready? Go. Okay, so there we have our experiment. First thing I need to do is to zoom in on just the collision. And we had a little bit too much energy. It almost came apart, which makes me think that my data probably won't be looking perfect. But let's zoom this thing in. Zoom this thing in. So right now I'm zoomed into just when the carts were moving. But just when the carts were moving is not when my collision occurred. I need to zoom in on when the collision occurred. So when do you think the collision itself occurred? Okay, about 2.9. So I'm going to zoom in further to about 2.9. So I want to have about 3 data points before anything started changing and about 3 data points after things, whoops, did that wrong. About 3 data points after things were changing. So that's about right. I don't know what happened there. That is not that well. It's probably because they didn't stick quite right because Nathan and I did a bad job. Moving this is.
So you're okay with us asking a lot of questions and helping us throughout?
Of course I'm okay. That's why would I be opposed to helping? Okay, so if we look at this, I have 3 lines on here. I have the total line, that's this line right here. I have cart 1's momentum and cart 2's momentum. Yeah, that was cart 1. Okay, somehow Somehow cart 1 and cart 2, well, let's, ooh, I may have misidentified where the collision is. You know why? Because my cart 1 and cart 2, one is positive and one is negative at the end. That cannot be. I must have missed where my collision is. Let me keep looking. There's my actual collision. Now it looks like it should. So you see, even I, the cocksure teacher, can make errors in judgment on these things. So if we look at this, I had momentum 2 was negative rather than positive. So I had which one, or momentum 1, excuse me, was negative rather than positive. So I had that backward.
Question on the graph.
Ask your question.
Where is it that we see that difference in mass having an effect on the graph? Like what?
Well, let me show you what effect it would have. Let's go back to changing this to 1 instead of 0.5. The entire graph shifts. See how the entire graph changed? So now that line is a very different height, the turquoise one. So I need to have the right mass or else the graph is just wrong. So now I have my collision. I have about 3 data points before the collision, 3 after. Cart 1 was up here at about 2.8 kilogram meters per second for its momentum. Cart 2 was about -2. 2.8 versus -2. They weren't equal speeds, but that's not going to be a problem. Does this look like my prediction? I have a bigger one on top, came down, they're the same at the end. Well, the same speed, not on top of each other. And was momentum conserved in this case? By the way, you do want to scale these so it takes up pretty much the entire vertical and horizontal space. So, and I don't want this on top of my graph, so I'm trying to grab this thing so I can move it. There we go. So was my total momentum, this red line, did it stay constant or did it go up or down?
That red line stayed constant.
Okay, so that means my momentum experimentally was conserved. What about the green line here in kinetic energy? Did it stay constant or did it go up or down? So kinetic energy was not conserved. So now I have my data. Now, make sure that you take a snapshot of this. Make sure you take a snapshot of this so you have a record. And especially for the first time you do it with your group, call Nathan or me over for just clarifying that you're reading the right thing, looking the right place in your data, making the right judgment. So now that I've done this, I'm going to go back to the lab guide, and I'm going to put in for my experiment 5, Richard, momentum, C for conserved. Kinetic energy, NC for not conserved. Each one of you, when you are done with your trial, I want you to come up and add your information here. And then you're going to write down everybody's information in your lab guide. You understand that?
Can you scroll up and keep scrolling and just stay there? No, scroll down. Just like, yep.
Remember, yours are not the same as mine.
So we're not supposed to write that.
No.
Well, you're answering for your situation.
Your prediction's going to be different. So like mine, where it's equal mass and part 2 is initially at rest, it's going to be different than yours. But I don't know what it would be.
Our computer, you can actually even, it's not set up like it's not working.
Okay, so after we finish with the instruction, we can get that straightened out. All right, now I'm doing 2 trials, so let's do my second trial. I'm not going to fill in this box again for the second trial because, well, I don't have space for it. But my second trial is unequal mass cart 1 catching up with cart 2. So now, unequal mass, I'm going to leave my masses as they are. But now, Nathan, you can push them both. He's going to push this one faster than this one, so it catches up and collides. Everybody with us? Okay. So I am going to delete this data because I've taken a picture of it, and I made sure it was the right place. Go for it, bud. Okay.
Do we have it on the wrong side?
One of them got turned around. I was going to talk about that later, but yes, you cannot turn it around. So this one here. I'll talk about that later, so you guys know what we're doing. Okay, farther apart to start with.
No, please come.
All right, so there we did where this one caught up to this one. The heavier one caught up to the lighter one. So now my data, that doesn't look right at all, does it? First thing I do is just auto scale it so I can see the whole experiment. And now I have to determine, where did the collision occur? Vanessa and I both agreed last time, and we were wrong. Can you tell when it occurred in this experiment? You're going to be right this time, Vanessa. When did my collision occur?
1.2.
1.2.
2.2.
1.2 is when Nathan was pushing.
Okay.
2.2 is roughly where the collision occurred. So once again, I need to zoom in to just that time. So there we have just the time of the collision. Scale this for the vertical.
I don't know how to run this computer.
Well, you will learn as we go through lab. All right, so if we look at these, look at the momentum graph. Does that total momentum, the red line, look about constant? Yes, so I'm going to say yes, momentum is conserved. Does the green line here look about constant? I'm going to go with no, because it started up here around 0.2 and then it dipped, and then it was kind of level again afterward.
So this would be for elastic.
So no, this was unequal masses, cart 1 approaching cart 2 for inelastic still.
Oh, you did.
Right, I'm doing 2 of them. So there I've done my portion for the first inelastic cases. Now I go through and do everything again for the elastic case. So you're once again going to make a prediction. Well, here you answer questions. Was your prediction right? And so on. But then you're going to make a prediction and draw your predicted graphs here. Put your reasons and whatnot here. And then we're doing these. So just to make sure we're clear, Josie Rogers, Jessica, can't remember her last name. Nephew. And Vanessa Taylor, Annabelle Harper, Richard Webb. There we go. So now I'm going to do the same 2 trials, but I'm going to change them from inelastic to elastic. What was the key on elastic versus inelastic? Elastic, they bounce off each other. Inelastic, they stick. If you put this cart here so the plunger is facing the other cart, the Velcro will hold them together. If you turn it around, then you have magnets that will make them repel. Now, if you push them so hard that they touch, so if you hear something during the collision, you just need to do it again, because then it was not an elastic collision. So we are going to reproduce the same 2 experiments, but now with them set so they will repel. You ready, Nate?
That's the very last page.
That is.
That's the inelastic one?
No, that is elastic.
Okay.
Also, so
Go ahead.
if like I do my experiment and everything, and I do my initial question and everything, and then we all turn these in, and we're all doing each other's experiment.
Mm-hmm.
Let's say I missed mine, but the rest of the class doesn't miss theirs.
Mhm.
Does my grade take down the rest of the class?
No, your grade won't take down the rest of the class, but do, especially for the first one you do, make sure you talk to Nathan and make sure you're doing it right. Okay, so I took a snapshot of my second one. Now I'm going to clear the data, and Nathan and I are going to do the third one. So here we go, Nathan. Believe it or not, I think that was a little too hard still. So we're going to try it again because I could hear something when they hit. Okay, go. Okay,
Don't expect no.
I tried. I think you're right, but do I have a collision here? Oh, you can clearly see the collision, right? Any question about where the collision is? 5.4. You knew what you're talking about. So now I once again zoom in on that collision. Notice that I adjust the scale so it's going to completely take up the screen. Oh, I see what's going on. Friction being friction and all, I got a little carried away. The reason we zoom into only like 3 data points is because otherwise friction will lead you astray. Notice how much friction was changing my values before the collision. That's a little bit troubling, right? But that's just part of what's going on. Friction exists. So I need to go a little bit further. Yeah, that's good. So now, one thing to note here is when the collision actually started. Because of magnets, the collision was not as short in time as it was for the inelastic case. My collision actually started somewhere around here, and my collision ended somewhere around here. Now, if you look at this once again for the red line for momentum, does that look like it was conserved or did it change?
It changed near the end.
It actually looks like it went up a little at the end, right?
Yes.
But during the collision, going from here to here, it pretty much stayed constant. So conserved. Now my kinetic energy is this green line, total kinetic energy. It's dropping, and then it comes back up.
Not conserved.
This one is supposed to be conserved, but I would answer the same as you did.
Should have been.
It should have been conserved in theory, but my experiment seems to say it wasn't. Why does my experiment disagree with what I know it should have been? It disagrees because of friction.
Do we have to put down why the experiment disagrees? Because your girl's not gonna know that.
Ask me,
Okay.
because your boy knows.
We gonna.
So the way to generally judge this is consider the straight line following the total before the collision and the straight line following the total after the collision. If there is a jump, then you say it's not conserved. If the line before and after match up, then you say it's conserved. It does definitely, it's always going to drop in the middle because you change kinetic energy to magnetic potential energy during the collision. But then it should have given it back. So I'm going to our data and I'm putting conserved and not conserved, even though I know this should have been conserved. I'm putting what my data said. Right? I'm not making up data. Okay, last trial by Nathan and I, and then it's your turn. So Nate, catching up. And remember, don't forget to take pictures of your data. Don't forget to scale it right, because I was a little sloppy there. Take a picture, and then delete my last data run, and start her up. It's got to catch up, Nate. Bueno, that was perfect. Well, until the end. Yeah, I know. That's where I said until the end. Okay, so what should I do now? What's the next step I should do?
Take a picture.
Not yet. First, I have to auto scale it first so I can see my data and see where the collision was.
You're a genius.
Now that I can see where the collision was, tell me, what time was my collision?
3.6.
How about 2.5 or 2.3? 2.3 is where the collision was. This here at 3.6, that's when I stopped one of them. And then the other one was going and hit it. That was also a collision, but not my collision. So now I need to scale it to that.
Girl, I don't know. I think we could all work on one together and we'll probably figure it out.
Unite.
Wait, what?
You know, wink, wink.
No.
I do. Okay, but see, can you share?
Okay, so here we have my data. Now, once again, the red line. Is the red line a nice continuous line, or did it have a jump?
It jumped down.
What's that?
It was a nice continuous line.
Oh, that red.
You-
There's two reds.
Are there two reds?
There's
No,
one
there's
red
purple.
and 12 red.
Purple
No,
and
not
red.
the purple on the second one. And kinetic.
You're seeing this is red?
Red, mine.
Okay, anyway, so my momentum line, nice and constant. My kinetic energy line,
Yeah.
if you look at this one, this fits within my understanding of constant. So for this, I will say both were conserved.
Because I'm saying whether it's gonna be or will not be.
So there I have done my experiments. Then you have questions on your prediction here. And then finally your conclusion. What did you learn? What were you supposed to learn about today?
Whether kinetic energy, momentum, and kinetic energy are close together or something like that.
Whether they're conserved in elastic and inelastic collisions. So make sure what I learned talks about what you learned, if you actually achieve that goal.
Yeah,
So
but
now
what if we
it's
don't?
your turn. Well, if you don't, make sure you're asking me questions so we can actually be successful.
What if it's like we were supposed to learn this, but I did not quite understand it, and so therefore
Please.
we are just needing to redo the experiment at some point Sunday.
Or you can ask questions today and we can work our way to understand.
Okay, so my first question.
What's
Where do I start?
You have your prediction. You have your prediction that you got
What
it
is
right
this?
now. I don't know. Don't.
What is this?
Okay,
What
so
is that?
what did you-
What is
You
that?
might need to stay right here.
No, don't be smart. What is that? What do I need to do with that? Nathan. What am I supposed to write?
Yeah, I know, but I don't want to.
Like, are we supposed to do those
Oh,
questions or only our other
Like what?
questions?
Yeah, it doesn't matter, practice, you're right. It's still.
What? Girl,
So,
I hope so.
it'd be so.
Because I know how equally don't use smart, so you.
Okay. Doesn't look well, okay, so. Only one card, right? So,
Wait, no, it's this. It's okay if you don't.
I thought you said you're doing one where it's just one card.
You can like wait.
Yeah.
It's
I was just trying to.
Oh, look, I'm learning how
to scroll.
Oh, good.
I'm gonna mash them up.
Then let's make it work.
0.6.
First, I'm gonna make sure I move this away from the track, so let's do this. So let's try it. So Vanessa, go ahead and pull it all the way to the end. But you have to try, you wanna go end to end.
I do have a question. Oh, you have a question? Oh,
I have a question.
I have more than you know.
Okay, go for it.
What is this?
That's probably not hard. Also, you need to make sure you pull your hand back so it doesn't measure your hand.
We have to pick it for teaching.
Oh, I know why.
Because this is what they're teaching in eighth grade
Make
right
sure
now.
you pull your hand back.
And so we have to have a basis knowledge.
Teaching is in one yes.
Okay,
I
so,
don't remember really.
oh, scale this.
I'm
So this here is when I grab it. That doesn't matter.
And then again, I didn't even remember
So
when I
I have
did it there.
So I have to scale it.
So
Well, you can't tell them. Because that spike will be grabbed. Okay, so you could see.
the will it be changed, basically, not changed.
So if we look at
And
this,
I say that it will be changed. Just
you
change.
see that, okay,
Just
there's a certain
changed.
area that doesn't lead when you're super close. So you have to go like at least this far. That's what you're seeing with this stuff. But through here, it looks fine because you have two lines right on top of each other, and this one doesn't. So that's fine, but then you have to answer your questions.
Reason, Nathan, are you gonna let me off if I put my reason
So
and
what are
don't
your
know?
questions?
Just put your reason down.
Yeah.
I'm going to have to,
Straight line.
but
Okay, so was it constant?
We wrote it up. The
Girl,
line was constant.
I know the 5 people
So-
in my education
You're telling me that
classes,
this
It's
number
there.
here is the same as this number here?
Frick.
that is it.
I thought they would down if they go up.
You guys talk about?
No.
Well, because it's totally
I mean, we don't like to talk about that. It's pretty awesome. There's some stuff with it.
Okay. So with communication concern, you can scale down so you can see it. What's your question?
so just the first step.
Yes.
Yes.
And then they do the ones that were assigned.
Yes, we get the ones that were
So the total is
assigned,
the one that's twice.
Yeah, so for the first one,
So the total drop.
just to make
Just
sure.
roll
that-
it in, just, okay, but that was answer my question. What do I do?
Why based on theory?
So-
or why based
We
on-
can split it out, right?
After-
Put words in there?
So, yeah, after we end that, so, you answer these questions for this.
Okay, so then this is.
All right, let's do it.
Those are your predictions.
Ready?
And your reasons.
No, I'm not even over my thing.
Come on, speed it up.
So
No, I'm not
you're
even ready
joining
now.
this. Why do you think that?
Do you have it ready?
Ready, set, go.
Why is so many? Yes. So there's your reasons on why I did. That's why we're focusing on
So we
just a
have to do it
short
again?
time, so yeah,
Right?
friction effect is not very big.
I don't think so.
I did it. It is done. This is what I have. I don't know what it
Three
means.
lines.
There are 3 lines there.
Oh, okay.
And so, the very first one was momentum conserved, not changed as your risk of parking. Roll down the track.
Where's this one?
So, yes, it was considered, but we did change it also, but with one line, all just straight.
What does that mean?
I mean, so, if you need to zoom in.
I have no idea how to do
Are we
that.
taking into account friction here?
So
Don't
first,
go over our head.
first you do this button to see the whole graph.
Sure.
And, okay, so we have these glitches here. Unless somebody, okay, you need to make sure this is not close to the traffic
That's
starter. And you need to make sure nobody has like their hand close to traffic to do it. So try it again because those glitches would be a problem in your experiment. Oh, and here's definitely another problem. See how this is not going straight?
Yeah,
Check that one, how's it angled?
straight.
Okay, so just delete the data you already did. Try it again.
Ready, set,
But
go.
doesn't need your hand video.
No, I'll just put my hand out when it gets there because I don't want to be in the way.
Ready, set, go.
Well, actually, you want to start it first and then have them push it because otherwise you miss the moving part.
Okay, I'll tell you when to go.
Just wait until you hear it click.
Go.
Okay, so this here's when I grabbed it. This was now fine. So now it's good. First problem heard. But now we need to scale this bad boy so we can see, right? It's too small now to see if it stayed constant or not. Right, you can't tell how big it is, it just looks really close to zero. So we need to scale it, so we first start by letting it do its own thing. Whoops, not this. And when you scale, since this is all above zero, we don't need anything negative.
Do it a little bit harder. You're gonna have to stop because you're on that side.
Okay,
Again,
so now we look at that total. And that purple line looked like it was staying the same height.
You're like,
No, no.
No, it didn't, so that means momentum wasn't conserved. Right, so,
Because it went down.
right. So if you're gonna put because it went down, and your reason to write it from the graph. Now we need to scale similarly for kinetic energy.
and this is which one? This is mine.
So does that kinetic energy look like it stayed constant throughout?
No.
No, what it is?
Um,
Now, theoretically, why do you think that those both went down?
Because it slowed down,
Why did it slow down?
because there was a force of friction pushing against it.
That's right.
Went on it. Was declining. We know because the line went down. That's the theory. The graph will know because the lines.
Oh,
The theory is the friction.
Yeah.
Graph is the-
I was gonna say, I thought we were
So what's the theory?
because when the car was rolling down on the track, friction and stuff, slowing it down.
Friction causes the car to slow down. Okay.
So you put no on both of those, right? No, no?
Yep. Now what?
So we saved this first graph.
The first one, I don't think you need to say, does it say?
Oh.
Did you already delete it?
Yeah.
Yeah, it doesn't say save.
Okay.
But save the others.
Okay, so we do my graph and then we do yours.
And then upload your graphs, just like you did last week. Save yours and upload yours to your Google account.
Okay, what's yours?
So mine is equal mass, part 2 initially at rest.
Okay.
So does that mean there's 2 parts on there and I'm putting one up there that's just standing there and then I push one that has the equal mass towards it?
Yep.
Okay.
This is why we.
That's the easiest one to do because you only have to push one part. Make sure you set the masses before you start. Did you already level it?
Yeah, we leveled it before we did it.
Okay, so you hit the calculator button. And set them both to 0.5.
Do I need to put that off or something?
No, it doesn't matter. And for this, you want it to be,
I don't know.
well, you want this facing that one, so they stick together.
Oh, because this one has.
That one's the
Those are
same
on
on
both
both sides.
sides, so it doesn't matter.
That one's called a collision card, this was called the dynamics card, the difference is.
Oh,
Is this not closer?
Well, first you have to.
Okay, ready?
Give me 1 second. So the kinetic energy will be
Yeah.
compared to the reason for that need.
I think
What was
the
this one?
calculation.
This is my theory, you don't have to write anything down for this one here.
I can help
At
you.
5.5.
Well, okay, I
What's the
said,
question?
it says that, the kinetic energy will or will not be conserved, and I have to give a reason.
What kinetic energy?
Scaling is trying to use this.
When kinetic is the impact,
Like it stays
You
still,
want the
so I
screen,
think
like, right now.
energy
it will be
will be.
changed because it's gonna be
You need to scale it down.
I think it
But
will
you
be
also want the
considered.
photo screen. So,
no, yeah, will be changed.
now, that's right.
No,
Now, we don't
conserved
want-
is the same,
There's nothing below
when it
zero, so
changes,
hold this
it's
down
not
so it's at the bottom.
right, Nathaniel?
And then
Oh,
we want to
it's
scale
smart.
out, so we have about 3 data points.
So it won't be
So
conserved.
yeah. So keep going, because see, there's a whole bunch here. So keep going till it's all the way here. Don't bring it back. Okay, so now bring it back. No, not. Now just go up here.
And I'm just trying to get it so it moves on or so they just stick together. Basically, so they stick together.
Which one?
It says the equal mass, part two initially
This
addressed.
doesn't relate anything. This here, so is this the inelastic or? Oh no, this is inelastic.
Yeah.
Okay.
Okay, so there we have the scales
Inelastic
properly.
means they don't.
Don't stick together?
It relates to the
Okay,
top.
so
Inelastic means
I
they
want them
don't
to kind of bounce back.
Inelastic means they stick.
Inelastic means
Yeah,
they
that's
stick.
it.
Okay.
Okay. Yeah. So that's how we're supposed to look.
Ready?
Take a picture now so we don't lose it.
Wait, I'll tell you.
And so then you answer questions. Which one's the total momentum? Does it stay constant or does it change?
That's
Just
my
got that.
That's my
Right.
baby girl,
Girl.
my woman. Yes. Okay, now what?
So now I gotta fill out the ones. With my
Yes.
prediction about
So
the
does that
product.
stay constant? or does it
I
change?
think I'm supposed to move this.
Yeah, you're supposed to do screenshots and move.
You're done with this one. Now it's your turn.
Look, I'm moving it.
We move it from zero, right? We start to find the zero and move it up.
You're talking about, okay, so you just did a collision?
Yeah.
Okay, to start with, do the auto scale thing so you can see the whole data set.
I did.
Because
Like what we did up there. You need to do that.
the collision's to the right of what we are. Yeah, the other way.
This one's a little shallow.
And so we just need to make it bigger.
And you need to scale, so you only have like 3 data points before and 3 data points after.
Ah.
The reason is because that will make the effects of friction not look so significant. Because you saw from the first one, the friction is going to be a big effect. So, right now, you get your last adjustment inadvertently not adjusted so we couldn't see it before. It should be about there.
So we just want 3 numbers over and 3 numbers behind. So we basically want that in the middle.
And then the final thing is to move these off the data. So they don't interfere with our view. Yeah.
Okay. And so, what's your
Did you
prediction about,
draw it?
do I have to draw it?
Yeah.
Well, you're supposed to predict before you do it.
Predict the drawing?
Yeah.
Oh, so I thought we were just predicting I can predict what I thought was gonna happen before the drawing, so I just thought it was gonna stay straight. I didn't.
Okay, yeah, so draw it there. The idea is to make sure that you've thought through what you think will happen and then you do it, what actually happens. So if they're different, you understand, hey, I didn't quite understand this. And is the stylus there? What?
Look at that. That's beautiful.
And make sure you take a screen capture of your nicely scaled graph.
How do you do that?
Okay, so now it's nicely scaled. Click on the camera. So click on it. There.
Oh,
So now,
no.
what's your prediction of
Oh my gosh,
product?
sorry, did you draw it? It's the first stuff on it.
Well, she hasn't gotten there yet.
Right.
Oh, yeah.
They're gonna go a lot faster than us.
Oh, yeah.
Heads up.
I'm.
So if it was equal mass and the second part was initially arrested, kinetic energy did change because it had to move. So it was constant.
You put what you think on this. This is your prediction, right?
No.
No, this is the,
Okay, so you've already got your predictions all done.
yeah, that's
And draw your prediction, I know.
She already
She does,
did
I
it.
can't, she can see. Okay, so now if we look at this, we just analyze the lines. Does this line here look like it changed or stayed the same?
It changed slightly here and then.
It does look that way. So once again, it's supposed to be a C, but it actually, it dropped from 0.15 to about 0.135-ish.
So it's not really.
So, well, it's small, but it changed. So I would put NC because, well, it wasn't perfect, right? We can't make up data. We can't say, oh, it's supposed to be this, so I'm putting what it's supposed to be.
Okay,
But
so
what
it would
is?
be not changed because it didn't change a lot.
Well, not conserved,
Not concerned, because it did.
because it
change.
did change a little bit.
So then for the kinetic energy, that's the green
Definitely
line?
not conserved.
Yeah.
Definitely not
yeah.
conserved.
Okay,
Okay?
so then. What, equal measure, can I have a release?
Well, she has to do hers.
Oh, what's going after?
But then how are we supposed to do the predictions, like, are we supposed to do these predictions while she's doing that, or what?
I don't care when you do them,
Okay.
just before you do your next one.
Okay. And then we say them all at once, or I'll do both.
Wait,
of them.
answer your question.
My question was, well, here's my question is, we took a screenshot of this, so I should do my second one,
No, have to do hers first.
okay. We'll do yours first, and I can answer.
Okay, have you
the-
done your prediction, Eva?
Oh, no, I'll do it.
So like for the elastic would be that they don't. They're bouncing,
Elastic is they bounce off
they
each
bounce
other.
off of each other. So my momentum will not be conserved in the it will not be conserved in the weakness. So will it bounce off of each other or not? And I would say no, because we Velcro on it.
Well, we're gonna turn this around,
Oh.
so the magnets make them so they should not touch at all.
Okay. Then yes, because the force between them will push them against each other. Back. Well, even if it's just sitting there, the force of one hitting another one, the force of the first one not hitting each other.
So, the predictions I want you to answer on your own. I'll help you with that after we've done the experiment and analyze it. I want you to think it through and just put what you think. Right, you're getting graded on the predictions on your thinking, not
So
on
we're
your
not gonna
predictions.
get marked off if the prediction was wrong.
Right, unless it looks like you didn't try, unless you just wrote random words, you know.
So,
Same with the
I'm
graphs,
down
you know, the graph should match what you write. And you should do yours at the same time, I don't know.
At the same time as hers.
Well, because you're doing a different scenario, you have a different set of things to consider.
We're working on it together.
I guess my question is, for the pictures, like when I'm screenshotting, I don't need this one and then my next one and then put my number and I'll just hers the next one. We just take all 4 pictures and upload them.
Well, what works easiest is if you arrange them so your 2 pictures are next to each other and hers pictures are next to each
So
other.
that's okay.
And then I can just split it and have 1 page for each.
Okay, so momentum will not be considered, the equal mass of card 2 is initially at rest, so the first part.
Same thing. Oh,
Well,
wait, this is the last
stage. Yeah, so
So this one's gonna be shown.
it's not conserved means it will,
Yes.
Not
Not concerned means it will.
so it will change because you have your force
Okay.
restriction and another one in the concept.
Yes.
I wondered, I thought you guys were whispering about it. Thought y'all were being mean, low key.
Well, we've
Good to know it was just that.
it was scared, I mean, we started moving that.
But sleep isn't working yet, so it like goes off in 2 hours.
Or like when I was trying to demonstrate, it goes off
The
immediately.
kinetic energy is the same because the card will bounce off of energy.
It'll be more drastic because every time we do a graph, kinetic is more drastic. Look at that.
Man, my dad used to ban those around.
I never had that option.
Just like you're facing.
Oh, yeah.
Give you a bloody
Your
nose.
graphs may probably look like they're, or it'll take a dip. It'll take a dip.
So the first part will.
It'll go and then I think it'll take a dip. I could be right.
Well, I gotta do some, what was the name of that card again?
Energy, with the energy around.
Wait for it.
Okay, so the momentum of the cart would go up, and then it would, like this, right? This is how I'm seeing it. Tai Chi!
No, you missed one of the all-time funny things.
Okay, so here's the story. So this man,
We're sitting at Taco Bell.
we're sitting at Taco Bell and across the street, this man pulls up into a parking lot with his Nissan Versa. He gets out of his car, he gets a bow stick. Well, no. Was that like a broomstick or something?
I couldn't tell what it was from that.
Anyway, he gets this thing and then he starts just doing this in the middle of the parking lot.
Me.
We're across Taco Bell.
I would die to see that.
Just sort of a kick and then
Yeah, and his kick was like that. It wasn't like
he's
he
like
was
there
actually
for a
doing
solid
it.
5 minutes doing this.
And he just started
And then he just gets in his car and leaves.
Man's
Why?
meditating.
Y'all be hating on him, and he was just meditating with that smell
Oh,
of
we were
Taco Bell.
hating, we were laughing.
Okay, so let's do this next one.
Ready?
That's why we're interesting.
And one more. Ooh, that's not gonna be a good one. Why didn't it bounce back? It was supposed to bounce back. Because I think it was
It was fine actually.
You sound like my sister. Yeah, because you suck.
Try again.
Girl.
Go.
Okay, yeah. Yeah, I would say that's it.
Ready? I'll tell you when. Go. Damn. Oh my gosh. What the hell?
Okay.
What is that?
That is a line. Well, kinetic energy stays the same. Or not kinetic, the momentum.
What am I supposed to do this again?
She copied the data from that table, from my two lines. I don't think that's what it is though for.
Dr. White, can you double check that this is correct, that was scaled?
I think it is.
Absolutely.
Let's have double check.
Oh no, you
It doesn't
can double check, but I think it is.
We're gonna do a discount double check.
I'm sorry. So I would say that my energy was not kinetic because it did change where it went down, and then I'm gonna have to load everything. Correct.
I'm gonna actually scale this to a little more time because the collision took longer than we think it did. So here we have, right now, there's about 3 data points after, but because the collision is longer for this one.
But it still went down, so it would still be my momentum would be non.
So for the momentum,
It goes down.
okay, so look from here to here and see how it's dropping. I wanna see if it basically stays on that trend.
Oh, dropping.
Because that's, the friction is what
So
causes
yes,
it.
it stayed on the trend till it hit it, but then it went back up, so it didn't have change, so therefore it would not be constant.
I would say it stayed on this trend for the entire time.
Oh, so
So
what
I'd
do
say
you,
that was constant. Now this one here, once again,
Maybe
look
not
at its trend
that
here.
far, because
And
And
that
say,
went
does it
down.
follow on that trend? Well, this was a downward
maybe
trend.
so yes,
So is it following down that trend? It dropped in between because it changed from kinetic to potential. It came back to the same, so
so
I'd
that
say
was
C
still
below.
constant.
Yeah.
Huh? Oh my goodness. Thank you, Annabelle.
Mm-hmm. What is it? C and NC?
No, C and C. And then I just take a picture.
Scroll to the
Not
bottom.
quite what you want to do.
Oh, before you remove these. And I finally figured out, you click on this white thing here, then you can move them.
It's C and C?
Yeah.
Yes.
How do I go back? Oh well.
Oh no, yeah.
Okay, now take it.
And I just got to.
Yeah, let's go check here and make back two.
Right there. So then do I just save both of those for mine?
Yeah, you can go ahead and do it now.
Do I want to do excellent? Oh, great.
Print to Microsoft. and do it. Yeah, make sure you do that. Number two.
Oh. I have a wireless printer. This is all new to me, this whole movement and just save the
Now
not.
it's gonna ask you to give it. So.
Oh, you're not.
Don't crush, don't crush, don't crush.
If it crashes, I'm gonna cry.
I think it probably did because it's stuck at 0%. It shouldn't be stuck at 0%.
That
Go
is-
ahead. I'm gonna go to the desktop. It's stuck there because we have. So go ahead and name it Josie Wood. It may or may not work having an apostrophe.
Oh, I didn't think about that.
You have disallowed.
Oh.
Good.
And then I can just clear out.
So now, yeah.
My turn.
No. But you could actually get rid of both of those.
Oh, by this.
Let's do one more thing before you do that. Let's go to the desktop. Where's the desktop?
Obviously, it's conserved for momentum. Yeah. But I don't think it.
Okay, so here's, nope, because they only have open it. Let's make sure it looks right. I'm always really concerned about like if you lose it. Like, oh, actually, no crazy.
Even in there, it's like.
Or you just give me an A.
There's always that. Okay, perfect.
And the thing is,
Then
that
you
you
upload that to the
Oh.
and you can do that later. I know it's good.
So the end is
It's grass because you got yours.
So
Josie's done. Annabelle hasn't started.
That was a
so
lot
goes down,
for
goes back up again.
what?
It's conserved.
You gotta fill these out before you do anything. Do your
So-
line
I
and
feel like
From
my
the
grammar,
fourth
this
floor.
one's just gonna do. I don't think that's something.
Because you're out on the straight line here.
I already took it.
this is that's what it is. Girl, I have to ask Nathan because I have to get a screenshot. Please, she needs to have manners.
So
Sorry,
we
sorry.
look at this line. So you see it's going down just a little bit. And then say, okay, that continue to cross because they wouldn't match up. So unequal mass rest. So that's how you judge.
Oh, damn. Oh, wait, which one's doesn't have
Just as long as you give it some thought.
Wait, which one has the heaviness?
It's supposed to be this one. But if you put it in this one, just make sure you make it so it's part two that has
Oh, okay.
one program in the front.
Figure out. These, what do you want us to do with screenshots? Let them talk to you and
Yeah,
figure out what to do.
just give it a thought, so you have all four of the screenshots done.
Okay.
Why do I think?
So which two are hers and yours?
Because
Jessica.
art.
Oh, okay, excellent. So, Jessica, Vanessa,
I equal mass. What is your equal mass? You have equal mass, right?
Thank you.
Equal mass means that they're the same weight. So one will be heavier than the other. So it's gonna push more than the other because one's gonna be heavier than the other.
just fast, of course.
So that's what I would do up here. Now for
You'll
your momentum,
remember in 10 seconds approximately.
one mass, since one mass is heavier than the other, the force of the heavier object is gonna push the
Now
No,
go
left
to
one.
that, go to Moodle and upload that file for Lab 3.
Did you guys finish up your last one?
They did.
Can you write it up there so we can give them a minute?
Oh, I was gonna mention, I hope you guys have been looking on Moodle at your return lab guides. And I've been trying to make sure I answer as many of the questions as I can, make sure we're on track. Because people have been answering questions wrong, and that's not my goal at all. My goal is for you to understand, not for you to lose points. So, if you're unsure on things, just what you ask.
All right. You can ask.
I'm gonna start it off like this. Ready? Go.
Make sure you. Yeah, you also put your hand up there, probably interfere.
Well, do you want us to read it or?
I would probably do it, yeah.
Scale it, you said, so we.
As you did set cart 1, since you put in cart 1 to be 1 kilogram. Okay, do that before you scale it, because it will change your scale.
Okay, so this one, right here. That's 2.5, one, I would change it to 1.
Well, cart 1, because it was more than 1. Change that to 1. Okay, now close that. Now, this here's obviously, let's start with that. Where's the collision?
Right here.
Real obvious, good. So then,
Scale that. How much do you want me to scale it?
you want to scale it, so you only have about 3 data points before, 2 data points after the collision. And then so you use the whole height. I usually do the time first.
Oh. You want to scale it so that's 3 data?
So first go up to that,
Oh.
and then drag it to the left.
3 data points before would be like 2.2.
So it'd be like 2.45. Okay, so now go down like you go on the axis. Well, that way you want to go up the vertical scale. There. Now come down to here. And then you can drag to the right. Hang of it,
A little bit.
go.
How far, yeah, how far
You want about 3 data points before the push and 3 data points. So actually, go down to see that. We have about 6 before or after.
do I see?
So drag a little bit to the left and stretch it. Let's get to the left and stretch it. Yeah, that should be good. And then you can rescale. This one first pull it down because this one's and actually, that's right. Now, last of all, click on the light field there and just move it somewhere so it's not in the way. And that's it.
Thank you, Dr. Webb.
So now take your screenshots and where's your question?
how do you delete the screenshots?
Okay, make sure you don't delete hers, of course. Click on this, and then you'll actually say.
That first one's yours, there you go. What was your prediction again? Either? So the red line is what you're looking at for the top. Did it stay or did it go down at all? Did you say it was gonna stay the same or change?
It was gonna stay the same.
So then that's what you would say.
No. The momentum. Which goes down.
If it goes down, it means it's not conserved, correct?
If it doesn't stay on the same trend.
Yeah.
So if it was going down before, it stays on that same down. So like, see here, this was going down. It just stays on the same trend, so you'd say that's conserved because it stays on the same
So
trend.
was the same, so you could say that it is C, not NC.
And let me say, I like the way that you're helping her. Not just trying to answer, but asking her the appropriate questions for her to think it through.
Yeah. Oh, I already did. I don't know. Maybe they're expecting us to write it in. They didn't have hers, but they already turned it in the left, so.
They should have waited to have that.
Okay, we're just curious on that.
I was like, wait up for what that is.
So now we can.
Right.
Alright, last one. Wait, we did that right. That first one right? Because inelastic, they're not supposed to hit, right?
Inelastic hits are
Any elastic that hits stick together.
If you- What is that?
You can actually look at your graph and tell.
Oh,
See how you've got this dip in between.
So they didn't stick,
That was
so
the
just
elastic.
change this to the elastic, not inelastic. So for your elastic, you're gonna put down what you wrote there. That. Can she, Dr. Webb,
Yeah.
so she wrote for, hold on, she wrote for her inelastic.
Yeah, I understand the problem.
Could you
I
just
would
write
really-
it down on the side? Like this is inelastic and then flip it over and the other side is elastic.
Yes, to make sure it's really clear, so when the grader gets there, they know what's going on. Because if the grader doesn't know, so both of them need to have rotations. Otherwise, there will be, this does not match, 0.
That's obvious.
Yeah, yeah. And then on the other one, make sure you do some of them. Because we grade them one question at a time for all of the students. We don't even know whose we're grading. So there would be no thought to check the other one unless you have a mark on both.
I said just change the letters. Everything I'll have to change.
This one?
On the other one. On the last.
I want to change the word.
Yeah.
What's got the answer to these?
Okay, so do those really quick.
Well,
No, you
after
just,
the trial.
yeah, after the trial. I'm
But
still
that was
answering
elastic
mine.
one.
The last one was elastic.
Correct.
This one's inelastic. So you already
Oh,
filled out
okay,
this
okay,
one,
okay.
so you just need to flip it. Yeah, there you go. And once I save
Oh,
it there, we can do
that was
the
tragedy.
Tragedy. Muy bueno.
The doctor left, I wanna make sure I'm doing this right.
Oh, lab's half over.
Half over.
Yeah.
Oh. So I'm doing that correctly.
It ends at 5, that ends at 5.
Thought I did it 4.
Well, 4.
Correct?
It depends on which one you're looking at, what it says. It's a 3-hour lab.
Is that how I wanna scale it?
No, because you can't see before. You only see during and after. So what you want to do is get the hand and drag to the right. That far. So bring it down, so you have about 3 to 4. So this one here is good. Okay, that's good. And then come down here and scale just a little bit there. And finally, no, that's good. Finally, get back out here to even raise it so you can see.
What if it's like half and half?
And then do I need to make this bigger?
No, that's perfect. And then this one here needs to be adjusted. Let's see over here. There you go. And then move these out. Okay, that was pretty clear cut, right?
Yeah, there you go.
All right, well, that one, energy was not conserved. I said it was not gonna be, look at it going, jeez.
You put that in the wrong column.
No, she put it in the right column.
She put it in the momentum column.
Yeah, we can talk about
No, it's not.
it. It goes down. Red line, right?
But not a lot. Remember how if it's continuous, it doesn't count?
I mean, it starts at the top and it goes to
Yeah,
the
but
bottom of it.
see the downward slope it has here? It's fairly consistent with that.
That's how
Right,
we
that's-
look
that's-
at it.
Because of friction, if we had no friction, we wouldn't have to make that as a rule. It's like, what's she, oh, yes. And this one here. Okay, make sure you fill that up there.
Oh, no.
Get that.
I'll save yours and then I'll upload it.
Well, upload hers to her report.
Yeah, I'm just saving it on here first.
And I should get the homework done tonight, Jessica.
Thank you. I only ask because I work all weekends, so I never have time to do it on weekends.
Yeah.
Make sure it's there.
There's a lot of drawings on my tables.
There are actually. Quite a few there.
Makes me wonder if the janitors ever wash the tablettops.
Yeah.
I know I don't.
Well, yeah, it's real gross.
So can I start from Subway?
I slept for 3 hours today. I hope that.
I totally forgot there was some the other today. So I was annoyed for it.
I get you down
Poor Amy was so exhausted last night
from.
from all of the work she did getting ready for it and then having the banquet. She was like incoherent trying to talk to me.
Oh, I'm gonna download my software. Oh, that I accidentally pressed Microsoft before I pressed.
Do you want me to write mine in?
Yes.
Can you do the inelastic because I didn't get any of those, so I need those.
Let's see.
Okay, and I'll sign out so you can sign in Annabelle.
Okay. Are you talking about this one? Yeah.
Yeah, what was yours for that one?
CNC.
Thank you.
Mhm.
CNC.
CNC. There you go. Yeah. NC.
C for both. Or it's hard.
Okay, I need to finish my question. This one, down.
Most of it was concerned.
It was on
Conserved in the markets, candidates.
No, this is for mine.
Oh, yeah. Well, it's talking about the lab, not specifically yours. Like the table,
Oh.
based on what you wrote in the table. That is what